Hi, my name is Ali Shesava from Bode Digital. In this short introductory video, we're going to look at how we can assess the stability of our power supply by just looking at its Bode plot. Okay, so in order to assess the stability of our power supply, we often look at its Bode plot. The good news is that the Bode plot is usually given. Either you are looking at it on a design software such as Bode WDS, which is the one that we'll be using in this online class, or you are using your own software. Again, the Bode plot of your design will be given, or you are measuring it perhaps with a network analyzer. So what we need to be aware of is when you look at the Bode plot, what do you look at to assess the stability? And you'll be glad to know that it's a lot simpler than most people think. But first, very quickly, where Bode plots come from. Well, we have done a couple of other in-depth videos of where these come from. But for now, just for this introductory video, let us quickly discuss what happens when we assess the stability in frequency domain. Let us for simplicity say that you just have a simple RC filter. And let us say that I inject a sine wave here and I look at the sine wave that comes out there. For simplicity, let us say that I am injecting a 1 volt sine wave with a frequency of 10 hertz, right? Okay, there's really only two things that can happen to this sine wave if I put it through my system. Let us say that one, its height can change, and two, its phase can change. So I have got a 10 hertz 1 volt sine wave. I am putting it into that network, and there you go, that's your 1 volt 10 hertz. Let us say that by the time it comes out, its height has doubled or half, doesn't matter. For simplicity, let us say that it has doubled. So I put in 1 volt and it comes out at 2 volts. Then my gain would be 2 volts because the one that has come out is 2 times the size that it's gone in. So I can go to my plot and I plot that at 10 hertz, my gain was 2. There we go. And then I do it again at 20 hertz, 30 hertz, 40 hertz, and all the way, and I end up with a gain plot. Now, in our particular case, it was a low pass filter, so that height would be smaller. It would look like this, where this is 0 dB. Remember that we plot things in dB. Again, we have done another video on how you convert from normal linear gain to dB, and it shows how this height will change. The other thing that can happen is that there will be a phase shift. So again, let us say that I inject the same 1 volt 10 hertz sine wave, and now in addition to a height change, there is also a phase shift. Again, for simplicity, let's say this is 90 degrees. There's a phase lag of 90 degrees of the sine wave that came out with the respect of the sine wave that I injected in. So in addition to knowing that the gain was 2, I now know that there is a phase lag of 90, and of course I will have a second plot. That was initially was my gain plot, and now I have a phase plot. And I would go and say at 10 hertz, the phase lag was minus 90 degrees, and then I do it again at 20 hertz, 30 hertz, 40 hertz, and I'll go all the way up. So I end up with 2 plots, a gain plot and a phase plot. Again, I stress in this day and age, actually, we don't plot these by hand anymore. Either our software, WDS design software, will provide you the Bode plot for you, or you're measuring it with a network analyzer. Now, when I have got these 2 plots, then I only have to look at 4 points on this plot. One of them I call the crossover frequency. At another point, I'll be assessing what's called phase margin, the slope at crossover frequency, and the gain margin. Finally, this is not part of the stability, but I want to have a high gain, a high dB at lower frequencies. And that's it. So if I look at these four for my stability, and this is actually for good regulation, I can assess the overall performance and in particular the stability of my power supply. So I'm going to show you a real example, and it's probably better shown on the computer. So we're going to go on the computer and we're going to assess the stability of a control loop of a power supply. Okay. So here we are looking at the Bode plot of a real power supply. The green trace is my gain plot. The red trace is my phase plot. And as I mentioned earlier, the computer is providing this for you, or you're measuring it. You just need to know what to look at in order to assess the stability. The first thing that we look at is the crossover frequency. That is the point at which the gain plot crosses the 0 dB axis. Remember I said we inject a sine wave and we look at the size that it comes out. A 0 dB is a gain of 1. That means that the sine wave that I put in came out same size because my gain is 1. So this point at which the green trace crosses the 0 dB axis is called the crossover frequency. Now that is very, very important because phase margin is defined at my crossover frequency, and also crossover frequency determines how fast my power supply recovers in transient, after transient in time domain. So the higher the crossover frequency, the faster the transient response in time domain on oscilloscope, but it is harder to stabilize the power supply. A good value for a crossover frequency is 1/20th of your switching frequency. So if your power supply is switching at 200 kilohertz, then a good value for crossover frequency would be 10 kilohertz, 1/20th of your switching frequency. At crossover frequency, which is my, at this point is 10 kilohertz, I look at my phase at 10 kilohertz, and I will look to see how far above minus 180 degrees my phase is. You can see here that my phase is around 45 degrees above minus 180, and this is what we call phase margin. Now, a phase margin is a measure of my stability. The closer I am to minus 180, the closer to instability I am. And therefore, I want a phase margin of better than 45 degrees. Typically, we aim for around 55 to 60 degrees of phase margin. Then another point that we need to look at is the slope of the gain plot at around 0 dB. So as it crosses, we would like the slope to be shallow at a rate of around minus 20 dB per decade. We don't want it to be sharp because, again, that means that our power supply may be approaching instability. This one is a little bit hard to measure by hand, but again, the good news is that power supply design software such as WDS, or when you make a measurement, the computer actually will make this measurement for you and will show you what the slope is. What I'm not showing here is the gain margin, because gain margin is not usually a big problem in analog power supplies. However, for completeness, we will define the gain margin at what is our gain at phase being minus 180 degrees. So in this particular case, my phase hits minus 180 degrees at around 70 kilohertz, and at around 70 kilohertz, this is around 15 dBs below zero. So I've got a gain margin of 15 dBs. Typically, I want better than 10 dBs, which is great. But as I mentioned, even though the software will give it to you in analog power supplies, in my experience, it's not usually a problem. And then finally, the gain at low frequencies, look at this 100 hertz frequency, you'll see that the gain is around 50 dBs. We would like to have ideally a high gain at low frequencies. That's not because of stability. It doesn't really impact our stability. It is more the case of a high gain at low frequencies means that we have got a good regulation. And that's what we look at, not for stability purposes, for good regulation purposes. And that's it. Now, as I mentioned earlier, if you are taking the online workshop, you'll get a license for Breacher WDS, which not only gives you this familiar look of this Bode plot, but also assesses all the 4 important points that we are looking at. You'll see that here the crossover frequency is 20 kilohertz, phase margin is 60 degrees, gain margin is 27 dBs and the slope is around 22 dB per decade, a minus 22 dB per decade the slope, and therefore the power supply is a nice, stable power supply. Okay, so final summary, what we're going to look at. One, you're looking at crossover frequency. Typically, we try to aim for 1/20th of the switching frequency. Many books do say 1/10th. You can do so. It's just that passing the EMC test will be a little bit more difficult. 1/20th is nice conservative design. Phase margin of around 55 to 60 degrees, certainly better than 45 degrees. Shallower slope of between -20 to -30 dB per decade at crossover frequency, and a gain margin of better than 10 dB. In order to achieve this, we need to shape our Bode plot to look like this and meet the stability criteria. We use something called a compensator, and we're going to discuss how we design one of these for a buck converter in the next video. So I hope you've enjoyed this video. If you're taking the online workshop, you'll be doing several assignments on this, so you'll be very comfortable with looking at the Bode plot and assessing the stability. If you are watching on YouTube, please download the presentation, which will give you more examples. Thank you very much for watching, and I hope to see you in one of our workshops.